This video is about, this lecture is going to be about convolutional neural networks. But let me start with something called data augmentation first. Okay. Say we want to make the trained network robust to noise in the input. Okay. This can be done in the following manner. Uh, it can be done by taking the input data, say images X, adding some noise to the input, namely getting some x plus epsilon, and then adding this corrupted data to the training data set while having the same outputs. Okay, um, this allows us to potentially reject noise. So we will, if the original data is x as inputs and y as outputs, the augmented data set is going to be x as inputs with y as outputs and x plus epsilon or x plus error or x plus noise as input and y as output. Okay. Um, what this means is that the training process gets to learn the fact that a corrupted image or the corrupted input um, also has the same output y. So training on the augmented data set will help the resulting neural network to learn to ignore the noise and still predict the correct output. Okay, because that aspect is embedded in the input data itself. Okay, the augmented input data. On a related note, um, we've already discussed, like MNIST, for instance, has these numbers exactly centered and roughly the same size. Um, so if you want to somehow generalize, um, say, whatever neural network training in a manner that the network is able to find the numbers wherever they are in an image, then you could approach that problem by using data augmentation as well. You could augment the data with sort of translated versions of the objects or rotated versions of the objects in the input images, and then the output, of course, if like the input has these threes in different positions and the output is still three, the training of the network will make the network potentially learn, if the network is sufficiently complex, will allow the network to learn that all these things are the same object, three. Okay. Um, so using this kind of data augmentation, we can potentially give the resulting network what's called translation invariance. Okay, invariance. What does that mean? Translation just means movement without rotation. Um, and invariance means it doesn't change. Translation invariance means that translating the object within the image doesn't change the output. Namely, you just get the correct answer that it's a 3. Okay, so that's called data augmentation. Basically, you're taking your given data and then applying some transformations to it, adding some noise to it, or translating it, rotating it in a manner that you somehow have more data that allows you to solve sort of more complex problems or make the algorithm more general. Is there another way of giving neural networks this kind of translation and invariance? And that's the topic of the next, well, few pages, I guess. So convolutional neural networks, sometimes called convolutional nets or conv nets, CONV nets, or CNN, not the news channel. So lots of names, are an attempt at least approximately endowing translation invariance to the matrix, to the neural networks. Okay. Okay, let's jump into it. So far, we've used fully connected neural network layers. Okay, so we had a bunch of neurons, another bunch of neurons, and usually these things were fully connected. In other words, every neuron here is connected to every neuron on the next layer. Um, and if we have sufficiently wide, fully connected neural networks, of course, they're sufficient to approximate any function given sufficient depth or sufficient width of the neural networks. Um, However, especially for image recognition, it is thought that one can do better. Not in terms of the flexibility of the neural network, of course, because um, fully connected layers give you the greatest flexibility because everything is connected to everything else, and what else can you ask for? But um, but potentially we can change the architecture to make the neural network somehow more effective or efficient. Um, so the basic intuition is as follows. Specifically, let me motivate it with this kind of translation invariance where you have this object in different parts of the image, same object potentially. So because an image may have the same object or the same features within quotes in any part of the image, what do we want to do? Um, we want each part of the image to be analyzed in sort of the same way, perhaps, right? Um, Maybe in some way, images, maybe the top pixels are systematically different from the bottom pixels, like the sky versus the ground or something in panoramic pictures. But perhaps we want to analyze each part of the image with the same lens, if you will. Okay. Um, at least, at the very least, even if that's not all you do, at the very least, such an analysis should be part of the full analysis of an image. Okay. Um, so what you could do is scan, SCAN, this is a C, scan the whole image looking for a particular object or a feature. Okay. When we say feature here, we could mean some high-level object that you're looking for, like the eye of a person or face, or it could be something low-level like horizontal line or a patch of green color or whatever. Could be anything. Okay. But more importantly, maybe we want to do some kind of scanning, sort of the whole image. Okay. And convolutional neural networks build in this kind of scanning into the neural network. And when we say scanning, we mean moving through the whole image and sort of doing the same operation through the whole image. Okay. Um, and Before I talk about convolutional neural networks, let's talk about convolutional filters. And it turns out that if you take a vibrations class or a signal processing class, or uh, most of you have taken controls and system dynamics classes, you already know what a convolution is. Fourier transforms and Laplace transforms are convolutions. In vibrations, there are Green's functions that um, tell you what the solution to a differential equation is. It is used in terms of a convolution. Anyway, so very classical mechanical and aerospace engineering concept. And it's the same concept, but now used for these machine learning sort of situations. Um, okay, so what's a 1D convolutional filter? Fourier transform and Laplace transform, at least the continuous version, or for continuous signals here, we are looking at discrete number of points, although there is something called discrete Fourier transform and discrete Laplace transforms. In any case, all I wanted to say was they are also convolutions. Um, so say we want to analyze, let's first talk about 1D convolutional filter, and then later on we will talk about convolutional filters on images. But for now, we'll do 1D convolutional filters. Say we have some input vector, x equals x1 till xn, and then we want to apply a convolutional filter y equals y1, y2, y3. Okay, so these are all real numbers. So how does this work? What does it mean to say convolutional filter y equals y1, y2, y3, which has size 1 cross 3? So doing the convolution of x with y gives you the following new vector or array z. I just happen to use z here. Don't confuse it with the z that we've been using in the past, although this, I guess, is similar. Um, okay, z equals x convolution y. There is unfortunately no like universally accepted standard for convolution. I think in the vibration textbooks, some of the classical engineering textbooks, they would use a asterisk, like a star. Um, I put a circle around it because asterisk also seems to be used for multiplication. So maybe we don't want to use asterisks. But anyway, so that's a convolution. I'm just using that to represent a convolution, and people online seem to be using it for a convolution. Okay, what is this new vector z or new array z? You take y and then take the first three elements of x and take the dot product of y with the first three elements. And that's basically going to be your z1. So z1 is x1, y1 plus x2, y2 plus x3, y3. Dot product of the first three elements in the filter. Similarly, z2 is the dot product of elements from 2 to 4, x2, x3, x4, and y1, y2, y3, okay? And so on and so forth. Zi will be xi plus 1, xi plus 2, dotted with y1, y2, y3, okay? So essentially, what are we doing? We are taking this y, which has three elements, and then focusing on this part, taking the dot product with it, get z1. Focusing on this part, taking the dot product with it, z2. Focusing on this part, taking the dot product with it, z3. So we are essentially scanning the whole vector or the whole array with this filter, which people might sometimes call a kernel, Kernel. Unfortunately, the word kernel is used for too many different things, even in machine learning. So I kind of hate that word, but it's called a kernel. Um, in any case, uh, this particular, so what we're doing is scanning. What I mean by scanning is moving through the whole vector and taking dot products step by step. Okay, so the resulting z is basically a sequence of dot products that's obtained by scanning. Doing this generally results in a new vector, like we do z, that is smaller than x or y. Okay, in this particular case, we will actually get if x has n numbers and y has three numbers, z will have x minus 2 numbers. Okay, sorry, n minus 2 numbers. So what people often do is add a couple of numbers, add like an extra a zero on either side of either the input or the output z, so that the output z has the same length as the input x. Okay. So once you get the z, add like zero before and zero after or something like that. So that the size of the matrix doesn't decrease. It's not super important. Okay, so that's called convolution. That's 1D convolution. We can, I'll just talk about a couple of convolutional filters. If y is equal to minus 1, 1, then next time convolution y gives you x2 minus x1, x3 minus x2, etc. Right? Very simple. That's all it does. You take the dot product of this with the first two elements, namely x1, x2, you get minus x1 plus x2, which is this thing. So what this convolutional filter does is basically take the difference between consecutive elements. It's like doing diff of x in MATLAB. Okay, so why would that be useful? Why would the result of this diff operation be useful? If you scan through the outputs of this convolution and look for which differences are large, well, it tells you when things change suddenly in X. Okay, so it's a way of looking for jumps or edges. This is a different convolutional filter. Y has three elements here. Here it just had two elements. It could have how many other elements? Um, Here you have three elements, 1, 1, 1 times 1 over 3. Um, and the result of convolution with x will just be x1 plus x2 plus x3 by 3, x2 plus x3 plus x4 by 3, etc. So all you're doing is a moving average. This would be called a moving average filter, which is actually a command in MATLAB called smooth, um, where you're just producing a new vector by averaging a few data points from the old vector, okay? A few elements of the old vector. And of course, you can have more elements, like it can be 1, 1, 1, 1, m times, and divide by 1 over m. That works. Okay, so convolution is a linear operator, okay? If you have the input x, the output z is just some matrix times the input, and the matrix is basically this thing, okay? It's the same thing repeated, shifted, repeated, shifted, repeated, and so on. If in this case, if you had like y1, y2, y3, a 1 by 3 convolutional filter, of course, if you have more elements in y, then you would have y1, y2, y3, y4, y5 repeated, okay? So it's just a linear operation. Convolution is just like matrix multiplication, except it's sort of a very, very special kind of a matrix with essentially the same, it's a banded matrix, and it's the same thing repeated along the diagonal. Okay, so it's a very, very, very special kind of a linear operator, is what a convolution is. A general linear operator would be this matrix, and that would have, I don't know, if it was a matrix of n minus 2 times n, it would have that many elements, roughly n square elements if n is large, and potentially n square different numbers, approximately. But if you construct a convolutional linear operator, then it has only a few numbers that define the full linear transformation. So it's a very special kind of a linear transformation, okay? So that's all about 1D convolutions, and let me talk about 2D convolutions in the next video.